Light, a fundamental element of our universe, has captivated humanity since the dawn of time. It illuminates our world, enabling us to perceive the beauty and complexity that surrounds us. From the earliest civilizations to the present day, light has held a profound significance in our collective consciousness. Ancient cultures often revered light as a divine entity, associating it with knowledge, life, and creation. Think of the Egyptian sun god Ra, a powerful deity who embodied the life-giving energy of the sun. Consider the Greek god Apollo, often depicted with a radiant halo, symbolizing his association with light, music, and truth. These ancient myths and beliefs highlight the profound impact light has had on human thought and imagination throughout history. Despite its ubiquity, light remains an enigma, a phenomenon that defies simple explanation. We encounter light daily, yet rarely do we pause to contemplate its true nature. It is both familiar and profoundly mysterious, a constant presence in our lives that we often take for granted. Light is intangible, yet it possesses the power to illuminate our world. It is invisible, yet its absence plunges us into darkness. How can something so ethereal have such a profound impact on our perception and our very existence? The quest to understand light began in earnest with the ancient Greeks, who were among the first to grapple with the nature of vision and the properties of light. These early philosophers, driven by a thirst for knowledge and a desire to comprehend the world around them, developed a range of theories, some insightful and others ultimately flawed, that laid the groundwork for future scientific inquiry.
One prominent school of thought, championed by philosophers like myself, believed that light emanated from the eye itself. We envisioned the act of seeing as akin to shining a lantern into the darkness, with rays of light streaming from our eyes and illuminating the objects around us.
This theory, while intuitively appealing, struggled to explain several key phenomena. For instance, if our eyes were the sole source of light, why would we experience darkness at night? And why would we need external light sources like torches or the sun to see clearly? As the Greeks delved deeper into the nature of light and vision, they began to recognize the limitations of human perception. They observed that our eyes, while remarkable organs, are not infallible instruments. They can be deceived by illusions, tricked by darkness, and overwhelmed by excessive brightness. These observations led philosophers like Lucretius to question the reliability of our senses. In his epic poem On the Nature of Things, Lucretius argued that the world might be far more complex than our limited senses could perceive. He suggested that tiny, invisible particles, which he called idola, emanated from objects and entered our eyes, creating the sensation of sight. Lucretius's ideas, while rooted in the atomic theory of matter, represented a significant departure from earlier Greek thought. He shifted the focus from the eye as the primary source of light to the object itself, proposing that objects emitted something that interacted with our eyes to produce vision. The torch of scientific inquiry, passed down from the ancient Greeks, found its way to the Islamic Golden Age, where scholars like Alhazen, also known as Ibn al-Haytham, made groundbreaking contributions to the field of optics.
As a polymath with expertise in mathematics, astronomy, and physics, I challenged long-held beliefs about light and vision, laying the foundation for modern optical science.
In his influential book, Book of Optics, Alhazen meticulously documented his experiments and observations, demonstrating conclusively that light travels in straight lines and that we see objects because light reflects off them and enters our eyes.
This revolutionary insight overturned the emission theory of vision that had dominated Western thought for centuries. My experiments were both elegant and insightful.
He used a simple device called a camera obscura, essentially a darkened chamber with a small hole, to demonstrate that light travels in straight lines. By observing the inverted image projected onto the opposite wall of the chamber, Alhazen provided compelling evidence for the rectilinear propagation of light. As Europe emerged from the Dark Ages, a renewed interest in classical learning swept the continent, ushering in the Renaissance. This period of intellectual and artistic flourishing witnessed a resurgence of scientific inquiry, with scholars eager to build upon the foundations laid by ancient thinkers like Alhazen. One such scholar was the Polish astronomer Nicolaus Copernicus, who, in the 16th century, proposed a heliocentric model of the solar system, placing the Sun, rather than the Earth, at the centre. Copernicus's revolutionary idea, while initially met with resistance, sparked a revolution in astronomy and paved the way for a new understanding of the cosmos. The invention of the printing press in the 15th century played a crucial role in disseminating scientific knowledge during this period. Books, once rare and expensive, became more widely available, allowing scholars across Europe to share their ideas and collaborate on new discoveries. This newfound accessibility of knowledge fostered a spirit of inquiry and debate, leading to rapid advancements in various fields, including optics. Scholars began to question long-held assumptions about the nature of light, seeking empirical evidence to support or refute existing theories. This shift towards observation and experimentation marked a turning point in the history of science, paving the way for the scientific revolution that would transform our understanding of the natural world. While the particle theory of light, championed by ancient Greek thinkers and later revived during the Renaissance, offered a plausible explanation for some of light's properties, it struggled to account for others. The observation of phenomena like diffraction, the bending of light around obstacles, and interference. The interaction of light waves to create patterns of light and dark challenged the prevailing notion of light as a stream of particles.
In the mid-17th century, I suggested that light might be a disturbance that propagates through a medium, similar to sound waves traveling through air. Though my ideas lacked experimental evidence, they planted the seeds for the wave theory of light.
Shortly after, Francesco Maria Grimaldi, an Italian Jesuit priest and physicist, conducted experiments that provided the first concrete evidence supporting the wave nature of light.
I observed that when light passed through a narrow slit, it spread out, creating a pattern of light and dark bands on a screen behind the slit. This phenomenon, known as diffraction, could not be easily explained by the particle theory, which predicted that light should travel in straight lines and cast a sharp shadow of the slit.
Grimaldi's observations were pivotal, challenging the existing particle theory and paving the way for a deeper understanding of light's wave-like properties. Section 3. A persistent enigma, the medium of light. The wave theory of light, while gaining support from experimental observations, faced a significant hurdle: the nature of the medium through which light waves supposedly traveled. Waves, by definition, are disturbances that propagate through a medium. Sound waves, for example, travel through air, water, or solids, while water waves are disturbances that propagate through water. If light were indeed a wave, what was the medium through which it traveled? This hypothetical medium, dubbed the luminiferous ether, was thought to permeate all of space, providing a medium for light waves to travel through the vacuum of space. The concept of the ether presented a number of challenges. First, it had to be incredibly rigid to support the high speed of light, yet it couldn't impede the motion of celestial bodies. Second, it had to be transparent and undetectable, as it didn't appear to interact with matter in any observable way. Section 1. A philosophical foundation for waves. The 17th century marked a period of intense intellectual ferment, a time when long-held beliefs were challenged and new ideas took root. The scientific revolution, driven by observation, experimentation, and a willingness to question established dogma, was in full swing, transforming our understanding of the natural world. Amidst this intellectual upheaval, the nature of light emerged as a central question, sparking a debate that would captivate some of the brightest minds of the era.
René Descartes, a towering figure of 17th century philosophy and science, played a pivotal role in advancing the wave theory of light. In his influential treatise Discourse on the Method, Descartes proposed that light was not a material substance, but rather a disturbance that propagated through a medium, much like sound waves traveling through air. He envisioned this medium, which he called the plenum, as a ubiquitous substance that filled all of space, providing a conduit for light to travel from distant stars to our eyes. Descartes' ideas, while groundbreaking, were largely philosophical and lacked the rigor of experimental verification.
Section 2. Huygens and the wavefront. Christian Huygens, a Dutch mathematician, physicist and astronomer, emerged as one of the most ardent proponents of the wave theory of light in the latter half of the 17th century. Building upon Descartes' ideas and drawing inspiration from the behavior of water waves, Huygens developed a comprehensive theory of light that could account for a wide range of optical phenomena, including reflection, refraction, and diffraction. Central to Huygens' theory was the concept of the wavefront. He envisioned light waves as a series of expanding spherical wavefronts, with each point on a wavefront acting as a source of secondary wavelets. These secondary wavelets, he proposed, interfered with one another, creating a new wavefront that propagated forward in time. This elegant concept, known as Huygens' principle, provided a powerful tool for understanding how light waves interact with matter. It could explain why light bends when passing from one medium to another, accounting for the phenomenon of refraction. It could also explain how light spreads out when passing through a narrow aperture, accounting for the phenomenon of diffraction. While Huygens and other proponents of the wave theory made significant strides in explaining the behavior of light, their ideas faced a formidable challenge in the form of Isaac Newton, one of the most influential scientists of all time. Newton, renowned for his contributions to mathematics, physics and astronomy, championed a rival theory of light, the corpuscular theory, which proposed that light was composed of tiny discrete particles or corpuscles rather than waves. Newton's corpuscular theory, outlined in his landmark work Optics, published in 1704, drew upon his extensive experimental observations and his deep understanding of mechanics. He argued that the rectilinear propagation of light, its ability to travel in straight lines, could be easily explained if light were composed of particles. Particles, unlike waves, would not be expected to bend or diffract around obstacles. Furthermore, Newton's corpuscular theory could account for the reflection of light, explaining it as the bouncing of light corpuscles off a smooth surface. He also proposed that the different colors of light were due to differences in the size or mass of the light corpuscles, with red light consisting of larger or heavier corpuscles and violet light consisting of smaller or lighter ones. The 18th century witnessed a flourishing of scientific inquiry, with researchers across Europe eagerly pursuing new knowledge and refining existing theories. The debate over the nature of light, far from being settled, intensified as proponents of both the wave and corpuscular theories sought to marshal experimental evidence in support of their respective views. This era of experimentation pushed the boundaries of scientific understanding, revealing both the strengths and weaknesses of the competing theories, and laying the groundwork for a more nuanced understanding of light that would emerge in the 19th century. One of the most significant challenges facing the wave theory of light was its inability to fully explain the phenomenon of polarization, the observation that light waves can exhibit different properties depending on the direction in which they vibrate. While some proponents of the wave theory, such as Huygens, had proposed that light waves were longitudinal, similar to sound waves, this view struggled to account for the complexities of polarization. In the early 19th century, the English polymath Thomas Young conducted a series of groundbreaking experiments that would ultimately tip the scales in favor of the wave theory. Young, a physician, physicist, and linguist, possessed a remarkable breadth of knowledge and a keen experimental mind. His work on the interference of light, building upon earlier observations by Grimaldi, provided compelling evidence for the wave nature of light and laid the foundation for the field of wave optics. To fully appreciate the significance of Young's double-slit experiment, it's essential to understand the underlying principles of wave interference. When two waves meet, they interact with one another, creating a combined wave that can be either larger or smaller than the original waves, depending on their relative phases. This phenomenon, known as interference, is a hallmark of wave behavior and is readily observable in various forms, from the ripples on a pond to the sound waves emanating from two speakers. In Young's experiment, the two slits acted as sources of coherent light waves, meaning that the waves emanating from each slit had the same frequency and a fixed phase relationship. As these waves spread out from the slits, they overlapped and interfered with one another, creating a pattern of bright and dark bands on the screen behind the slits. The bright bands, or interference maxima, occurred at points where the waves from the two slits arrived in phase, meaning that their crests and troughs coincided, resulting in constructive interference. In these regions, the amplitudes of the waves added together, producing a brighter spot on the screen. Section 3. Fresnel and the triumph of waves. While Young's double-slit experiment provided compelling evidence for the wave nature of light, it was not immediately accepted by the entire scientific community. Some physicists, still clinging to Newton's corpuscular theory, sought alternative explanations for Young's observations, proposing that the interference patterns might be due to interactions between light corpuscles and the edges of the slits. However, the wave theory of light received a decisive boost in the early 19th century thanks to the work of Augustin-Jean Fresnel, a French physicist and engineer. Fresnel, largely self-taught in physics, possessed a remarkable intuition for the behavior of light and a deep understanding of mathematics. His work on diffraction, building upon the earlier work of Huygens, provided a rigorous mathematical framework for understanding how light waves bend around obstacles and spread out from narrow apertures. Fresnel's most significant contribution to the wave theory was his development of a mathematical model known as the Huygens-Fresnel principle that could accurately predict the diffraction patterns produced by various obstacles and apertures. This model, which combined Huygens' concept of secondary wavelets with the principle of interference, proved incredibly successful in accounting for a wide range of diffraction phenomena, from the bending of light around sharp edges to the spreading of light through narrow slits. Section 4. The Ether's Last Stand. A waiting game for revolution. Despite the overwhelming success of the wave theory of light in explaining a wide range of optical phenomena, one nagging question remained. If light were indeed a wave, what was the medium through which it travelled? The hypothetical luminiferous ether, proposed centuries earlier as a medium for light waves, continued to elude detection, casting a shadow of doubt over the wave theory. Throughout the 19th century, physicists devised increasingly sophisticated experiments to detect the ether, hoping to measure its properties and confirm its existence. One of the most famous of these experiments was the Michelson-Morley experiment, conducted in 1887 by American physicists Albert A. Michelson and Edward W. Morley. The Michelson-Morley experiment sought to detect the ether wind, a hypothetical drag force that the Earth's motion through the stationary ether was expected to create. By measuring the speed of light in different directions, Michelson and Morley hoped to detect subtle variations that would reveal the presence of the ether. Section 1. Setting the stage. The quest for electromagnetic waves. As the 19th century progressed, the scientific community found itself grappling with a profound mystery: the nature of light and its relationship to other physical phenomena. The wave theory of light, firmly established through the work of Young, Fresnel and others, had triumphed over Newton's corpuscular theory. But a crucial piece of the puzzle remained elusive: the luminiferous ether, the hypothetical medium through which light waves were thought to propagate. Despite numerous attempts to detect the ether, it remained stubbornly hidden, casting a shadow of doubt over the very foundation of the wave theory. Amidst this uncertainty, a new theoretical framework emerged that would forever change our understanding of light and its place in the cosmos. In the 1860s, James Clerk Maxwell, a Scottish physicist of exceptional mathematical prowess, developed a set of equations that unified electricity, magnetism, and light into a single elegant theory, electromagnetism. Maxwell's equations predicted the existence of electromagnetic waves, disturbances in the electromagnetic field that could travel through space at the speed of light. These waves, according to Maxwell's theory, were generated by the acceleration of electric charges and consisted of oscillating electric and magnetic fields that propagated perpendicular to each other and to the direction of wave travel. Section 2. Hertz's breakthrough, illuminating the electromagnetic spectrum. Heinrich Hertz, armed with a deep understanding of Maxwell's equations and a passion for experimental physics, set out to design an apparatus that could generate and detect electromagnetic waves. His experimental setup, though seemingly simple, was a testament to his ingenuity and his meticulous attention to detail. Hertz's apparatus consisted of two key components, a spark gap generator to create electromagnetic waves and a loop antenna to detect them. The spark gap generator consisted of two metal spheres separated by a small gap. When a high voltage was applied across the spheres, a spark would jump across the gap, creating a burst of electromagnetic radiation. The loop antenna, placed some distance away from the spark gap generator, consisted of a wire loop with a small gap at one end. The quantum revolution, light's duality revealed. Hertz's confirmation of electromagnetic waves seemed to settle the age-old debate about the nature of light, firmly establishing it as a wave phenomenon. However, the dawn of the 20th century brought with it a revolution in physics, the quantum revolution, that would challenge this view and reveal a profound and perplexing truth about light, that it possesses both wave-like and particle-like properties. This revolutionary concept, known as wave-particle duality, emerged from the study of the interaction of light with matter at the atomic and subatomic levels. Classical physics, with its clear distinction between waves and particles, proved inadequate to explain these interactions. A new set of rules, governed by the principles of quantum mechanics, was needed to make sense of the strange and counterintuitive behavior of light and matter at these scales. One of the key experiments that led to the development of quantum mechanics was the photoelectric effect, the observation that light shining on a metal surface could eject electrons from the metal. Classical physics predicted that the energy of the ejected electrons should depend on the intensity of the light. Brighter light should eject electrons with greater energy. However, experiments showed that the energy of the ejected electrons depended only on the frequency of the light, not its intensity. In 1905, Albert Einstein, then a young patent clerk, provided a revolutionary explanation for the photoelectric effect. Unveiling the secrets of light, ongoing explorations. The quantum revolution, with its revelation of light's dual nature, ushered in a new era of optical research, one that continues to this day. Physicists, armed with the tools of quantum mechanics and driven by an insatiable curiosity, are exploring the properties of light with unprecedented precision and delving into the fundamental mysteries of its interaction with matter. One area of active research is quantum optics, a field that explores the quantum properties of light and its applications in areas such as communication, computation, and sensing. Quantum optics has led to the development of technologies such as lasers, which produce highly coherent beams of light, and single photon sources, which generate individual photons on demand. These technologies have revolutionized fields such as telecommunications, medicine, and materials science. Another exciting area of research is attosecond physics, which explores the behavior of matter and light at the attosecond timescale, or billionths of a billionth of a second. At these incredibly short timescales, physicists can observe the motion of electrons within atoms and molecules, providing unprecedented insights into the fundamental processes that govern chemistry and biology. Light's enduring legacy, a beacon in the quest for knowledge. The journey we've undertaken, tracing the evolution of our understanding of light, stands as a testament to the insatiable curiosity of the human spirit and our relentless pursuit of knowledge. From the earliest musings of ancient philosophers, pondering the nature of vision, to the groundbreaking experiments of modern-day physicists, probing the quantum realm, light has served as a constant source of fascination and a driving force behind countless scientific breakthroughs. The epic battle between the wave and particle theories of light, far from being a mere historical footnote, exemplifies the dynamic nature of scientific progress. It highlights our willingness to challenge established dogma, embrace new ideas, and refine our understanding of the universe based on empirical evidence. The eventual realization that light possesses both wave-like and particle-like properties, a concept that shattered the foundations of classical physics, underscores the profound and often counterintuitive nature of the quantum realm. Light's influence extends far beyond the confines of physics laboratories and academic journals. It has illuminated our world in countless ways, shaping our technologies, our art, and our very perception of reality. From the incandescent bulbs that illuminate our homes, to the fiber optic cables that carry vast amounts of information across continents, light-based technologies have revolutionized our lives. Beyond the horizon, unanswered questions and the future of light. Despite centuries of inquiry and countless discoveries, the study of light remains a vibrant and ever-evolving field, replete with unanswered questions and tantalizing mysteries. The wave-particle duality of light, while a cornerstone of quantum mechanics, continues to challenge our intuition and spark debate about its true nature and implications. One area of active research is the search for a unified theory of quantum gravity, a theory that would reconcile quantum mechanics, which governs the behavior of matter and energy at the atomic and subatomic levels, with general relativity, Einstein's theory of gravity, which describes the large-scale structure of the universe. Light, as a fundamental constituent of the universe and a force that interacts with both matter and gravity, holds the key to unlocking this elusive unification. Another area of exploration is the study of light in extreme environments, such as the vicinity of black holes, where gravity is so strong that it warps the fabric of space-time. Understanding how light behaves in these extreme conditions could provide insights into the nature of gravity and the evolution of the universe.